Hello everyone, my name is Felipe Herrera Ortiz and I am part of Group 3 of PPCR. Here I'm going to explain the basic concepts about meta-analysis. So first of all, we have to differentiate what's the difference between a meta-analysis and a systematic literature review. So a systematic literature review is just the qualitative synthesis of several articles, while the meta-analysis is a quantitative synthesis. So why we perform meta-analysis or systematic literature reviews? So first of all, we perform them when we got a knowledge gap. We don't know if an intervention A is better than an intervention B. So we want to assess that effect, that difference in the effect between both drugs or both interventions, and we want to pool all the effects of the articles to make just one big effect in order to gain more power and increase the sample size. So first of all, we're going to talk about a little bit about how to interpret a forest plot. So in the common forest plot, we will find to the left the articles and the years. We will find a line that represents the line of no effect. In this case, we're measuring odds ratios, therefore the no effect will be 1. So if an article, these are the articles, if an article, for example, these are the articles and this is the sample size. The smaller the sample size, the smaller the rectangle, the smaller the sample size. The bigger the rectangle, the bigger the sample size. So as you see, as the sample size increases, also the confidence intervals, that are these lines, start to decrease. The smaller the sample size, the wider the confidence interval. So we have to take this into account when interpreting meta-analysis. So here we can see that there are several articles that cross the null effect line, as you can see. So these articles by themselves, they represent no effect. This article represents no effect because it crosses 1. This article represented no effect because it crosses 1. As you can see here, the confidence interval in this one is from 0.5 to 2.2, and this represents the confidence intervals of the odds ratios. So as you can see, these articles represent no effect, but these are small articles, so by themselves they don't have enough statistical power. So we will require to mix more articles. So in here we include 2 articles that have a big sample size, therefore the confidence interval is small, and we can see that the confidence interval is really far away from the null effect line. Okay, so with the meta-analysis, what we are doing is that we are combining all these effects in order to retrieve a common effect, in order to increase the sample size of our study. This triangle, this diamond that is represented at the end, represent the pool effect of all these meta-analyses, and the lateral parts of the diamond represent the confidence interval. As you can see, the pool effect of all the articles has an odds rate of 2.2 here, and a confidence interval ranging between 1.9 and 2.4. Therefore, we can say that when pulling all these effects, we retrieve a result that represents a risk because it's beyond 1. Therefore, the intervention A represents a risk in comparison to the control. Okay. Also, another important topic is is how to analyze heterogeneity in the results in the studies. So we can have sometimes studies that retrieve, for example, let me clean this, studies that retrieve, for example, an effect that represent a risk, but others that retrieve results that represent a protective effect. So how can we analyze this data? So there's something that's called the measurement of the heterogeneity. We can measure heterogeneity with different tests, but the most widely used tests are the Cochrane's Q, the I-square, and the Galbraith graph. So first of all, we're going to start with the Cochrane Q. When we retrieve a result in a Cochrane Q that's less than 0.05, we can say that the study has a high heterogeneity. We have assessed heterogeneity with Cochrane Q. We can measure the degree of heterogeneity. So that's the role of the I-square. So with the I-square, it tells us the percentage of heterogeneity that the whole forest plot has. So if we retrieve a I-square that's less than 50%, we can say that the heterogeneity is low. If we retrieve an I-square that's between 50 and 75%, we can say that we got a moderate heterogeneity. If we retrieve a result that's higher than 75%, we can say that we got a high heterogeneity. So this is really important, because when we retrieve an heterogeneity, a low heterogeneity, we have to use the fixed effect model. We are going to talk a little bit about that later. When we retrieve a moderate heterogeneity and a high heterogeneity, in this both case, we have to use the random effect model. And the Cochrane Q and I-square are the most widely used. The Galbraith graph is not used frequently because it's actually it's kind of a subjective way of evaluating heterogeneity, but in general the Galbraith graph just represent in this part it represents the effect, and in this part it represents the precision. And we retrieve some lines that represent the confidence interval. So we can find articles that are here that represent a high effect with high precision, these ones. The precision is kind similar to the confidence interval. Articles that represent a lower effect, but there are some articles that overpass these lines that are the confidence interval. Therefore, we can say that these articles represent heterogeneity because they overpass the confidence interval. But it's more objective. So the most widely used methods are the Cochrane Q and the I-square method. Another important topic that I would like to, another important idea I would like to say is that when we use a fixed effect model, the overall weight of the study, the results, the articles that got a higher sample size have a really high weight when using the fixed effect model. But when we use the random effect model, the weight of the higher articles is reduced, and it's distributed almost proportionally among the other articles in order to balance. And if we are balancing the sample among articles, also the confidence interval may be modified. It can be turned lower because we're increasing and we are balancing the sample size in all the studies. This is what's going to happen if we use a random effect model. So we're balancing all the weights in the study and therefore their confidence interval. Another important topic is that when we perform a forest plot, we need to evaluate if these results are robust, and to do that we have to perform a sensitivity analysis. A sensitivity analysis is no more than removing just one article and calculating the effect size of the meta-analysis. It can turn like this, for example. It can modify. Then we perform the same. We leave this one and we remove this one, and we assess if the results remain the same or they change. For example, as seen, we are leaving these studies and we're removing, in this case, this one. This is a study that's not so big, so it maybe won't affect at all the overall effect. But if we remove, for example, a big study, such maybe removing this one, and we leave this, the effect can be turned like this. It can be overpass the null effect and become a protective effect. If this happens, we can say that the results are not robust because they change when removing this study. If we're performing a sensitivity analysis and we, for example, remove this one and we leave the others, and the results remain the same. For example, in this case, it remains saying that the drug A represents a risk factor. They are robust. And if we remove this one and leave this one, and if the effect doesn't change when removing each study, the results are robust. If the effect changes when removing one study, we can say that the results are not robust. This is an example of a plot to evaluate sensitivity analysis. So here, the way of interpreting this is just seeing the articles that are located to the left, and this we are measuring the effect with an RR, a relative risk. This is the overall effect of the pool effect of the articles without removing anything. And when we perform a sensitivity analysis, is Shunkao. It says Shunkao over here, so we are removing Shunkao, and when removing Shunkao, this is the overall effect that we retrieve, and this is the confidence interval. Is it clear? So, for example, we are performing a sensitivity analysis. Here we remove McBean, and when removing McBean, this will be the overall effect, and this will be the confidence interval. And we perform this with every study. For example, in this case, we are removing Yang-Sun Park and obviously leaving the other studies. And we retrieve this effect size and this confidence interval. As seen, when we are removing each study, the effect doesn't change because we persist with a relative risk that is more than 1. As seen, when removing this study, this is like the borderline. We can see that any of these studies overpass the null effect of 1. The lower effect that we can retrieve, the lower relative risk that we retrieve, I think is this study, and it's a relative risk of 2.3. So of the confidence interval. So we can say that these results are robust because they don't change when removing a study. Another important subject that need to be assessed in meta-analysis is the publication bias. So there are different ways to evaluate publication bias, but first of all, we're going to explain what it is. So normally, journals tend to publish studies with positive results. Therefore, if we perform an analysis of the literature, we will find more studies with positive results because they are published. But if we perform that, we are overestimating the effect because we are not including the studies that are negative, that are not published. So we have to include published and not published studies in order to reduce this publication bias. And as I mentioned, we can evaluate publication bias different ways. The first we're going to explain is the funnel plot. So normally the funnel plot is a graph like this one that has a pyramidal appearance. So we are measuring in this part the effect size. It is normally measured in form of a standard error, and here we're measuring the effect size. It is measured normally in form of relative risk or odds ratios. We're talking about a categorical variable. So as I said previously, when we increase the sample size, if we increase the sample size, we will retrieve a smaller confidence interval. The confidence interval is pretty similar to the standard error. The standard error is just when applying inference statistics, but it's pretty similar. So for practical terms, if we have a smaller sample size, we will retrieve a wider standard error. So if the standard error is smaller, for example in this scenario, and when we are going down, the standard error is increasing, we are assuming that these studies has a smaller standard error because they got a higher sample size. Because they got a higher sample size, they got a smaller standard error. Right. So once we are decreasing, the standard error is increasing. Therefore, these studies got a smaller sample size because the standard error is wider, and the effect size is increasing. The odds ratios, or the relative risk in this case, is increasing when we turn to the right. So maybe here 5, 4, 3, 2, 1, and so on. So when interpreting the funnel plot, we have to understand how it looks. So this line represents the overall effect. These lines represent the confidence interval, and each dot over here, each dot represents an article. Okay, so for example, interpreting this is an article with a high sample size because the standard error is relatively small, and these articles And this is a study with a higher sample size, but with an effect that represents a risk, because the relative risk is just uplining and close to this point over passes 1. For example, interpreting this study, we can say that it is a small study because it has a big standard error, but it retrieves effects that represent a protective effect for the intervention. So if normally the funnel plot must have a pyramidal appearance of in the distribution of the articles, but in this scenario we can see that in this space there are missing articles. And what does this represent? So this represents that we are missing, and there are not published studies that use a small sample size and retrieve effects that represent a risk, that represent that intervention is a risk factor. So this represents a funnel plot with publication bias. But the problem when evaluating funnel plot is that, as seen, is a really subjective way. It depends on the interpretation of the author. So there are other ways, and usually it requires a higher sample size, a higher number of articles included in order to distribute it well around the pyramid appearance of the funnel plot. But there are other tests that are used to interpret the publication bias that are more objective. So there is the back test. The back test is a test that usually retrieves high power when there are more than 25 studies included in the forest plot. So this test is usually non-parametric, so it's actually pretty difficult to retrieve a forest plot with more than 25 studies. So normally the back test is not used because it doesn't have enough power for most of meta-analysis. But we interpret that a back test has publication bias when we retrieve a p-value less than 0.05. This will be subjective. This will indicate us that the study has publication bias. There are other tests, such as the eager test. So the eager test is better for smaller studies compared to the back test. Normally, an eager test has enough power when there are more than 10 studies published in the in the forest plot. So we interpret an eager test. We have to see two values, and is the alpha value that need to be close to 0. For example, 0.1, 0.01, and so on. It needs to be close to 0 in order to say that there is no publication bias. If the alpha value is highly different from 0, for example 2, we can say that there is publication bias. Another way that both ways are usually combined is to see the p-value. If the p-value is less than 0.05, we say that there is publication bias. Another important subject I would like to talk is how to measure the effect of a meta-analysis. This is a really important subject, and we got different ways to measure the effect. It depends on the outcome that we are evaluating. So if it's a qualitative outcome, for example death or alive, or someone having the disease or not having the disease, if it's a numerical variable, of it's a time to event variable. So if it's a qualitative variable, in this we are including as well ordinals variables, we can use relative risks, odds ratios, risk difference, diagnostic odds ratios, and number needed to treat. Okay, so if it's a numerical variable, we can use the mean difference to pull the effect, and we can use as well the standardized mean difference. That's also called the Cohen D. The Cohen D, it's the same. And also we can use the G of H. That's actually pretty similar to Cohen D, but with some modifications. And if it's a time to event variable, we need to use hazard ratios to evaluate the effect.